Imagine this situation. You have a general-purpose transformer feeding nonlinear loads. If you load it to rated capacity, harmonic currents will raise the temperature beyond its designed thermal limits. That excess temperature will accelerate insulation aging and will shorten transformer life. Now suppose you don't have the option to replace it with a K-rated transformer. So, what option is left to limit the temperature rise? Derating. Right? But the real engineering question is, how much derating? That is exactly what this video will answer. You will learn a simple IEEE method to calculate transformer derating under nonlinear loads. Let's begin by understanding what actually changes when the load becomes nonlinear. With nonlinear loads, transformer current becomes non-sinusoidal. So, in addition to the 50 Hz or 60 Hz fundamental current, harmonic currents flow through the transformer windings. And this completely changes the transformer loss mechanism. Harmonic current components increase eddy currents in transformer windings, resulting in higher eddy current losses. And here is the key point, please remember this. Winding eddy current losses increase rapidly with frequency. That means higher order harmonics produce disproportionately higher heating. So even if the RMS current looks acceptable, the winding temperature can rise sharply. And this is why we cannot load a general-purpose transformer to its rated capacity when supplying non-sinusoidal currents. To deal with this problem, IEEE 57.110 provides a structured method to determine the derating factor. And it does this using one key concept: the harmonic loss factor. The harmonic loss factor is defined as the ratio of the total eddy current losses caused by harmonic currents to the eddy current losses at the power frequency, assuming no harmonic currents existed. In simple terms, it tells us how much extra winding heating harmonics are causing compared to a pure sinusoidal load. This converts harmonic distortion into actual thermal impact. The harmonic loss factor can be calculated using either of two IEEE-defined formulas. Quick note before we move on. The harmonic loss factor is similar in concept, but not identical, to the K factor defined in UL 1561. Both relate to transformer heating due to harmonics, but they are defined differently. We will cover a detailed comparison between harmonic loss factor and K factor in a separate video. For this video, let's stay focused on how IEEE uses the harmonic loss factor to calculate transformer derating. IEEE 57.110 provides two methods to calculate a safe derating factor. Method 1 uses design eddy current loss data. Method 2 uses data from a certified test report. In this video, we will focus on Method 1. To apply Method 1, you need two inputs. First, the load current harmonic spectrum. This tells us how much current flows at each harmonic order. Second, the winding eddy current loss at rated conditions, expressed as a fraction of the local I²R loss at the point of maximum loss density. This value is provided by the transformer manufacturer. Now let's apply this method to a practical example. Suppose a 2000 kVA general-purpose dry-type transformer is supplying a non-sinusoidal current with the following harmonic distribution. The transformer winding eddy current loss under rated conditions at the point of maximum loss density is 15% of the local I²R loss. The derating factor is calculated in two steps. Before we move further, here is an important point, please remember this. These steps are valid for dry-type transformers. For oil-filled transformers, the calculation steps are different. We will cover those in a separate video. Let's continue with the dry-type transformer. First, we calculate the harmonic loss factor using one of the IEEE formulas. In both equations, IH is the RMS value of the load current at harmonic H, and H is the harmonic order. In equation 1, I1 represents the RMS value of the fundamental load current. In equation 2, I represents the RMS value of the total load current. One important point to note here. The harmonic current to fundamental current ratio can be directly read from a power quality meter, which significantly simplifies the calculation using equation 1. However, both equations give the same result. Using either equation, we get harmonic loss factor of 3.2. Now we move to the final step. The derating factor, or in other words, the maximum permissible non-sinusoidal load current for this harmonic composition, is calculated using this equation. Here, Imax per unit is the maximum continuous load current, expressed in per unit. PLLR is the per unit load loss at rated conditions. PECR is the per unit winding eddy current loss at rated conditions. And FHL is the harmonic loss factor we calculated in step 1. Substituting the calculated FHL value and the rated loss data into this equation gives us a derating factor of 0.88. This means that, with the given load current harmonic spectrum, this dry-type transformer can be safely loaded up to 88% of its rated capacity. This is how derating is done correctly. So next time your transformer faces harmonics, don't guess the derating factor. Use IEEE 57.110. That is real engineering. Thanks for watching.